I didn't finish it. What's that?
All right, so we're going to keep talking about, go through the last virtual machine instructions and how we're going to translate them into assembly. So this is like the rest of, well, the majority of Project 8 really. So there's one thing that I wanted to clear up from last time first, and then we'll launch into the last instruction. So this is like, branching functions. Or I think your book just calls it like, what's the word? I forget the word. Anyway, there's kind of a word that like encapsulates all of that. It's just like stuff that makes the program not just execute the next instruction, but to go somewhere else, right? And so the one thing I wanted to clear up from last time, so we had this instruction label, which you give it some name. So this is a virtual machine instruction. It's not really an instruction, it's just kind of like telling you that you're labeling this thing. And I think I said, oh, we just translate that in assembly to, we just translate that to, you know, a label in assembly. But the problem was, we said that, well, what if multiple different things have the same name for their labels, right? Then you're going to be, that's not going to be good. Okay, but here's the solution. And your book talks about this in detail, so this is all in your book. But so we don't do that. We instead do function name $sign label. Okay, so what is this? So number one, we're going to make the assumption that any valid virtual machine program within a given function, there's not duplicate labels. Okay, so like, for example, we're going to make sure when we write our compiler that the compiler, when it's compiling one function, it will not generate multiple labels that are identical. That would just be ridiculous, right? So within a given function, the labels will be unique. Now there might be, in another function, there might be some label of the same name. But by prefixing the function name to the label, we make sure that labels from different functions will end up with different names. And the $sign, I think it's just a kind of arbitrary choice of a special character that's normally not allowed in virtual machine labels, but it is allowed in assembly labels. So the $sign, it means like you can't accidentally end up with a label that actually has this name because the $sign wouldn't be valid. So, Zach.
So in the when we are translating from like the VM code to the assembly,
yeah.
how do we know what function we're in?
Well, remember, there is literally a virtual machine instruction called function.
Mm-hmm.
That means we are now defining this function, and like the instructions that come after it are the definition of that function. So that's how you know. You're processing it. Remember, like at this point, between virtual machine code and assembly code, it's still kind of a linear relationship. Even though one virtual machine instruction can generate many assembly instructions, it's still, we just kind of like go through, we translate this, we translate this, we translate this. So just as you're scanning through, you say, oh, here's a function command. So let me, right, you probably want a variable that remembers what function you're currently in. And so you set that variable, and then you keep going, and when you get to a label, you just look up what your current function name is, and you stick that on the label like that. So, shouldn't be too hard. Okay. So that's just clearing that up. So now, functions. When we started talking about this a little bit last time, just to recall, we have three virtual machine instructions relating to functions. right? There's a function which takes the name of the function and a value which is the number of local variables that the function needs. There is a call, another function, and some n, which is the number of arguments. Right, so number of local, number of arguments, and then there's return. And we're going to spend some time going through these in detail, like how we're going to actually make these work, how we're going to translate them into assembly so that it does kind of what we expect, how we expect functions to work. One thing that other thing I'm going to mention before we launch into that, we're kind of going to assume at this point that in a virtual machine program, everything is a function. So just like Java, but unlike Python. So in Python, you can just have code that's not in a function, right? In Java, you cannot. Like everything has to be a class, and in a class, everything has to be inside of a function. So our language is going to be more like that, more like Java. It actually is pretty similar to Java in a lot of ways. So everything is a function, and so the question then arises, like, how do we even get started? Like, how do we get started and call the first function? Like, how does that kind of get started? And so this is something that you did not have to do for Project 7, but for Project 8, you're going to have to add this. Like, the tests for Project 7 kind of did this for you, but for Project 8, as you continue to extend your virtual machine translator, you have to do this. There's some Bootstrap code that has to go at the very beginning. So before you start translating the virtual machine code, there's a little bit of code you have to put, assembly code you have to put that just like gets things set up. So Bootstrap code that goes, let's see, at the beginning. The first thing is that we're going to set, let's see, where do I have this? Oh yeah. First of all, we're going to set the stack pointer to 256. That's important because, like, as soon as we start calling some function, it expects to be able to push stuff on the stack and do stuff with the stack. And if the stack pointer isn't initialized to where we're going to store the stack, then who knows? It's going to start writing stuff random places in memory, right? Not good. So we have to initialize the stack pointer. And then there's actually only one other thing we're going to do. We're just going to call the function called sys.init. Okay, don't worry about what that is. Basically, this is a function that's going to be provided by, by the operating system that is going to do some more setup potentially, and then call a function called, I think it's called main. So this is also very similar to Java, right? Java, you have to have a special function called main, and when the program starts, it looks for a function with that name and calls it. The same thing is going to happen here. Sys.init is going to do some setup and then call the main function. So, but this is all that you have to do. And of course, when I say call sys.init, we're gonna see how to do the call instruction in a second. So obviously, this is like a bunch of assembly code, but you can just use whatever function you write to translate this, and you can just also use that to translate this. Okay. Okay. There's one other thing that's going to be different about Project 8 that you didn't have to worry about for Project 7, which is that you can have multiple .vm input files instead of just one, but I'll probably talk about that at the end. Yeah, Daniel.
Do we need to worry about if SP starts at a value higher than 256?
What do you mean if SP starts?
So we said it equal to 256.
Yes.
What if it's, before we run this, it's at 270? Or is that not possible?
It doesn't matter. I mean, so remember that, right, in the model we're working with, right, it's kind of like the computer, to run our computer, right, we have some machine code that we want to run on it. imagine like, you know, the machine code is like on a read-only cartridge that we plug into the computer and then we flip it on and it starts running it. So like, you're kind of asking, what if the stack pointer was 270, like, you know, at the moment we flip the computer on? Who cares? I mean, it's just like there was maybe some random electricity floating around that made it equal to something, who knows, but we don't care. Like, it doesn't have any meaning at that point. We just need to set it to what it actually is supposed to be. Now, of course, on a real computer, you don't just like turn the computer on every time you want to execute a program and then turn it off when you're done, and then like turn it on for the next program, right? It's running multiple programs, and so of course, when a new program starts, it has its own kind of notion of what the stack pointer is, and it has to initialize that. But even then, like, it's probably like the operating system says, here, this is your memory, do with it as you will. And you're like, well, okay, this part of my memory I'm going to treat as my stack, so I'm going to set my variable that I'm going to use to represent my stack pointer to point to this. It doesn't matter what it was before, because it was just some uninitialized memory. Cool. Other questions? I should say sys.init is provided by the operating system. It does some extra setup and calls main. Yeah, and for this project, like all of the tests, they will like provide a function called sys.init, which is why this works, right? Eventually, we'll write this ourselves, but for now, it's kind of like being given to you. Zach?
So I've spent a little bit of time trying to figure out how to make the instructions that have to set, have to, like the comparison operations.
Right.
Trying to figure out how to not write a new, not write new loops just for setting things to either 1 or 0 every time, or 0 or -1 every time you have to like make a comparison.
Oh.
Is there any like dedicated? So the problem I was running into is that I have no way of jumping back to the instruction that I would have been at next without the or without storing that address in memory.
Mm-hmm.
But because we don't have like a space set aside for that, there's no way to store it without editing the stack.
Well, you can. There are a few temporary like registers, virtual registers 13, 14, and 15, I think, are available to.
But we don't know what's being currently used either by a program.
You don't know what.
Like if a program was using that and our code
no,
used
so
it,
it's
would
not.
it
So
overwrite it?
those registers are for you, as in the. There's like multiple agents here, and of course we are all of them, but at different times. So a program, like a high-level program, has no direct access to those registers. The only thing that would direct anything to use those registers is like when you're translating. The virtual machine code also doesn't have access to those registers, really, right? It has idea of segments, and then the virtual machine translator will translate it into assembly that puts those segments somewhere, right? But it has no way of like specifically saying how to use those registers. So really, it's like only at the point when you're translating the virtual machine code into assembly, if you wish, you may generate some assembly that uses those registers for some temporary purpose, right? Now, if so, right, you writing projects 7 and 8 are the only person that's ever going to use those registers, if that makes sense.
Okay.
So, yeah, if you want to store something temporarily, I'm not sure I completely understood what you were trying to do, but it certainly is annoying that the hardware has so few registers.
Mm-hmm.
You have to do some kind of intricate dances sometimes, like moving data around and storing it temporary places so that you can, or like doing some clever tricks to like, well, can I get away with only storing 2 values at once instead of 3. So. All right. Well, let's talk about these. So I first want to talk about how to call a function. Okay, first, from the point of view of the caller. Okay, so if I meaning like some virtual machine function want to call another function, from my point of view, what is it supposed to look like? Okay, and we're still at this point talking at the level of the virtual machine, like what's going on in the virtual machine. And then once we understand what it's supposed to look like from that level, then we're going to think about, okay, how do we actually make some assembly code to make that happen? So here's what I do. Number one, I push arguments on the stack. Right? I think we talked about that before. If I want to call a function and it needs 3 arguments, I first push the 3 arguments to the function on the stack, 1, 2, 3, and then I call the function. Okay, and of course that function will expect to see its arguments there, basically. Number 2, I call the function. Right, using the call instruction. And I tell it how many arguments did I just push on the stack. And then number 3, when the function returns, the arguments will be gone, and the function's return value will be on top of the stack. Okay, so it looks kind of like this. So I first here's arg1, arg2, arg3. So step 1 is I do this, and then step 2 I call the function, and then when the function returns, it will look like this. So in other words, I push some arguments, call the function, and then I just have to do a pop to get the result of the function, and I can do whatever I want with it. Okay? Make sense? Any questions about this? Yeah, Simon.
Would it be possible for a function to have multiple return values to them?
Nope. No, this virtual machine does not support multiple return values. In fact, there's very few languages, if any, that truly support multiple return values. Usually it's just like, well, really, does Python support multiple return values? It turns out it doesn't. It can just return one thing, which happens to be a tuple. So maybe this one return value is actually a memory address, and if you follow the memory address, you'll find some data structure there which has a bunch of data. Also, interestingly, at the level of the virtual machine, every function has to return something. So if you're in a function that doesn't have a return value, just push 0 on the stack when you want to return or something like that. So it just makes it simpler to not have to have a bunch of ifs. It's like, oh, if it returns something, if it doesn't, it's just no. The compiler will deal with that. We can definitely write functions that do or don't have return values, but when the compiler turns it into virtual machine code, a function that does not return something, it'll just make it return 0, and then it'll just pop it and ignore it. Just makes things simpler. Okay, so what about from the point of view of the the called function, or you might see people use the word callee, which looks really weird to me, but whatever. Well, what does that function see? Number 1, the argument, memory segment contains the arguments. Right, notice it doesn't say anything about stack. Right, so from the point of view, if I'm a function and I'm called, I don't really know what's on the stack. I just can kind of think of it as if I have an empty stack. Yeah, there is actually stuff on the stack below me, but I'm not supposed to do anything with it. But if I refer to the argument segment, that will point me exactly to wherever my arguments are stored in memory. So that's nice. I don't have to think about where they are. I just say, yeah, get argument 0, get argument 1. And obviously, the assembly code we write is going to have to figure out how to set that up so that it takes wherever those arguments are on the stack and figures out how to point the argument segment to the right place. Number 2, the local segment is filled with the right number of zeros. In other words, however many local variables that I said I needed, like when I am called, the local segment is nicely set up for me. It's the right size and it's got all zeros in it. And I can then, store whatever things I want there. This, that, and temp are undefined. In other words, I can't rely on what is stored in those things, right? But I'm free to use them. I mean, I guess, this and that, it means I'm free to reassign this and that to somewhere else and, use them however I want. And temp is temp, so I can just use it and put temporary things there. Okay? And then, before, I can do whatever I want, but then before returning, push the return value on the stack. And then, of course, I return. Okay. Make sense? Any questions about this? So once again, the point is that to virtual machine language functions, we're providing this nice, beautiful view of the world. That it's just like, here are your arguments, here's your local variables. Do whatever you want, and when you're done, just put the return value here, and then we will take care of the rest, right? Imagine but behind the scenes there's some hotel staff that's scrambling around madly to and they run out the door, and then as soon as they come out the door, just they stop in there to make everything look nice. But so yeah, we're gonna have to figure out how to make this all work. So next page. So how do we actually make this work? So I'm going to draw a picture here. Make sure I have enough space. So here's the stack, right? And of course, some arguments get pushed. Okay, that's what gets pushed on the stack first. Now, so some function has just, or some code has just pushed some arguments and then done a call. And so how are we gonna, what are we gonna do to be able to go jump to this other function? So number one, we have to be able to come back to where we were after that function is done, right? Because on the virtual machine level, it just says call this function, and the other function says return, right? So something has to keep track of where that code actually is so that we can jump to the right place and jump back, okay? So the next thing that's going to get pushed on the stack is the return address. Okay, that is where in the code should we jump back when the function is done. Okay, and that gets saved on the stack so that, you know, once the function is done, we can get that and know where to jump. Now, the other thing is, right, this function, like there's a function that's currently running. It has some local variables, it has some arguments, right? It has maybe like what it set this and that to some certain things. And when this other function that it called returns, it expects to see all that stuff the same as it was, right? But like, of course, the function that we're calling has its own local variables and arguments, and it might set this and that to some other stuff. So we're going to have to save the values of those registers so that we can restore them when we come back. Okay, so first we're going to push local. Okay, so that's the register that says where are the local variables for this function. We have to save that so that we can restore it when we come back. We're going to push, right, where are the arguments for this function? We're going to also push this and that. Okay, and then finally, we're going to make space for all the local variables. So local 1, local 2, local n. Okay, and then the stack pointer is going to be here, right? Once we push all that stuff on the stack. The new the local register is going to point here, right? So the function that's being called, when it wants to look up its local variables, it will be told to look there. It turns out that's on the stack, but it doesn't really matter. It's somewhere. And of course, the arguments are down here, so we need the arg register to point there, so that the function can get its arguments. So this is called a stack frame, right? It stores, you know, all the info for a particular function call. Right, it has the information needed for the function being called, and it also has the information needed to restore the state when that function is done. Great. And obviously, I mean, it's a lot of stuff, right? But this is all we need, all of that. And if you have multiple functions being called, right, you'll end up with a bunch of these things on the stack, right? So it'll be like a whole stack frame, and then maybe a function will like push some more things on the stack. You'll have like some data on the stack, and then if it calls a function, you have a whole other stack frame on top of that. And it keeps going like that. Exactly.
So the local arg this and that we're pushing onto the stack there are from the previous
The
function.
old ones, yeah. So I should say like,
and then
you know,
arg,
old.
local, and sp are for the new ones.
Yeah,
right,
so this
that
is
are
like
pointing.
arg new.
Okay.
New, yeah. Yeah. So we don't have to actually like, we're not going to change this and that. It's just like the function that's being called might change this and that, so we have to save the old values just to be sure that we can restore them. Yeah, and SP, of course, SP. We don't need to save the old stack pointer. I mean, like we're just pushing stuff on the stack and then popping stuff from the stack. So the stack pointer is just keeping track. I was just showing that's where the stack pointer ends up, of course, at the top of the stack. Okay, so you know what? There we go. I want more space on the side here because we're going to want to refer to this picture while we're figuring out how to do both like call and return. And so, okay, so let's think about, given this picture, So if I do if I see a call instruction, what assembly code do I have to generate that's gonna set up this picture? Right, so like before this, the stack looked like this, right? Before we see a call, right, the code had to already push the arguments. The stack is gonna be here, and then we see the call, and we have to set up this. Okay, so what should we do? Well, what's the first thing we have to do? Push a return address? Where are we going to get that return address? This is a little tricky to think about. See if anyone...
This is where the arg starts for the previous function.
Say that again?
Is return address where the old function starts?
No, so remember, this stuff is living in RAM, right? So like all these things, you know, arg, local, those point to addresses in RAM. The return address is an address of an instruction. Those all live in the read-only memory, which is the instruction memory, right? So it's a totally different thing, right? It's like basically the index of the instruction where we want it to jump back in our program. Zach?
Should we then, from like whatever function called it in our VM translator, should we figure out like if we're storing a variable like we were talking about earlier for the current function, should we save that name and use that as the return address?
Good idea. The problem is that would mean it would jump back to the start of the function. We don't want it to jump back to the start of the function. We want it to jump back to like the current position where it was when it made the call, right? And it should jump back to right after that. That's getting closer though.
So a new label then?
Yeah, we need to make a new label. Where would we put that label?
At 1 plus the function call, instruction call.
1 plus the, okay. Yes, but remember, we're talking about assembly instructions, right? Our call, this virtual machine call instruction is going to expand into a ton of assembly instructions. So it's not just like 1 plus.
Good.
All right, we'll hold that thought. I think, let's keep going, and I think at the end we'll come back to this, and maybe it'll maybe become more clear. So, I'll just put a question mark here for now. Where do we get that? Okay, well, next thing, we have to save the values of local arg this and that. So that's easy, right? We just push local arg this, that. Right, it's just literally like load the value of those registers and push them onto the stack. And of course, as we know, pushing something on the stack is not just one assembly instruction, it's a bunch. But you know, by now you probably have a function you can call, like a Python or Java function in your translator you can call that says like generate some assembly code for pushing something on the stack, right? So what else do we need to do? So we've now pushed this and we pushed these things. A few more things we need to do.
Set the location of the new arg and the new local.
Yeah, good. So we need to set the location of the new value for the arg register and a new value for the local register. Okay. So which do you want to do? How do we set local? Simon?
It's just the current stack pointer.
Yeah, good. So at this point, right, if we do it right here, we've just pushed all this stuff, and like the stack pointer right now points to right here. which is where we're about to put the local variable space. So we can just say, okay, right now, whatever the stack pointer is, that's what local is going to be. So yeah, that works. So we can say local equals sp. Okay. How about arg? How do we set arg? Matthew?
It would be SP minus the number of arguments minus that 5.
Yeah, 5, I think, right. Yeah, so SP is here, and we just say, okay, 1, 2, 3, 4, 5, plus however many arguments. If I just like subtract that from the SP, get back to here. Why didn't we just set arg like before we started pushing all this stuff? It would have been simpler. We wouldn't have to do all this subtraction, right?
We wouldn't be able to push the old arg?
Yeah, exactly. No, we have to save the old value of arg before we go about changing it, so yeah. And once we've started pushing those registers in the stack, like, it doesn't really help to like make the new arg before we even push this and that. It's like, well, might as well just push all of them and then deal with that. So yeah, so arg is going to be sp minus 5 minus, I think m is what we were saying was the number of arguments. Yep. And actually, right, your translator will see this instruction, and like there's an actual number here for m. So, like you can actually just go ahead and add 5 plus whatever this number is, and then just do sp minus that. So you don't actually have to generate like 2 subtraction instructions. You can like add these together, and then just generate an instruction to take the sp and subtract whatever that value is, right? It does get a little tricky thinking about like, okay, like there's different computations that need to happen. When can they happen, right? Because there's some computations you can do while you're translating stuff. There's other computations you need to generate assembly to do later because, so certainly like sp minus something, we don't know what the sp is going to be, so we have to generate assembly to do a subtraction for us. But the 5 and m we both know when we're translating, so we can do that. Okay, what else?
Now start pushing local stuff?
Yep. Why do I not have that written on here? Okay. Oh, I see. Well, it's okay. I see why. I mean, you could do it. You could do it either way. So the choice that your book makes, and I think I understand why, is that we're not gonna push the locals here, because that pushing like some zeros on for the local variables is going to have to happen every single time we call that function. And so it's better to have that happen like as part of the function definition rather than have it duplicated every single place we ever call the function. It just makes the code shorter. This stuff is going to be different every time we call a function, so we can't like only have this one place, but the local variables we can do. So all right, well then the only other thing left to do is jump to the function. And I think actually what your book suggests is when you make a label for a function, you actually name it with the name of the file that it came from dot the name of the function. That way, because all the functions from multiple files are all going to go in one giant assembly program. And again, if multiple files have functions of the same name, you do not want them to get confused. But again, the details are all in your book. Okay. So we do this stuff. We jump to that that other thing. right, when it returns, we want it to pick up right here, right after the call. So going back to this, right, how do we get the return address? We can just put a label here. So the last thing we put is a label. Or we'll just call it, you know, ret or something. And of course, you can't literally call it ret. You have to, like, we talked about last time, like you have some counter. Every time you need one of these, you like increment the counter and call it like ret2, ret5, so that they're all different, because you have to have a different one for each function call. Okay. And by the way, this is all like, if you have the second edition of the book, this is like pages, it's like 150 something to like 160, I don't know, around those pages. This is in chapter 8, I guess. Like it's got some nice charts, it's got a picture, it's got this picture. Actually in the book, it draws this stack like upside down. I mean, it's kind of arbitrary which way you draw it. Like, is there like a physical direction to memory? I don't know. You know, if you think of it like as a stack, and you physically think about stacking things up, it makes sense to draw it this way. If you think about the memory addresses that are happening, right, it actually starts at a small memory address and then goes up every time that you increment it. Maybe you think of memory starting at like 0 up here and going down. Or you could draw it going across the page. It really doesn't matter, and you'll see different things use different conventions. I just pointed out so that you don't get confused. Like, you just have to notice that it's the other way. Yeah. All right, how about return? So what does return have to do? So when we do a return, right, there's going to be one more thing on top of the stack, which is going to be the return value. And then maybe we'll draw that up here. So like, yeah, when we call it, it's not there. After it returns, the stack pointer will be 1 higher, and there will be the return value will be there on top of the stack. So what do we need to do? For one thing, we need to like pop all this junk off the stack, right? So it really should be all the way down to where the stack pointer is here. Because remember, from the point of view of the function that's calling something, it pushed some arguments on the stack, and then it made a call, and when it comes back, it expects to see those gone, and it just expects to see the return value right here. So notice one thing we're going to have to do is actually copy the return value from here down to here. Right, from where the called function put it to where the caller expects to see it. Okay. We also need to restore all of its registers, like local arg this that. We need to restore those so that when we come back, things will look consistent for the caller function. Then we also need to, of course, jump to the return address. Right. After we've done like getting the stack set up the way it's supposed to, then we need to jump here. So we're going to need to like save this somewhere before we pop it off the stack. Anything else we need to do? I don't think so. I think that's it. So here is how your book suggests doing it. There's multiple ways that you could do this. So the first thing is we're going to say frame. We're going to save the current value of the local register, which points right here. And we're just going to call it frame. Now, so what is this frame thing? You know, for example, we could put it in like, you know, R13, one of those temporary registers. You don't have to put it in R13 specifically, but we need to save that value somewhere, temporary. And the reason we're going to do this is so that then we kind of have this anchor to refer to stuff in this stack frame without worrying about, like, because we're going to overwrite the local register, so we're not going to have that to refer to anymore. We're going to be changing the stack pointer, so we won't be able to refer to that. But if we save that value, then we know kind of where this stuff is. Okay. We also need to save the return address, or save the return address. You know, and this would be another temporary thing. So like, I'll just actually frame and ret are temp variables. For example, R13 and 14. How do we get the return address? How do we know where it is? Simon?
Is it LCL -5?
Yeah, or we could say frame -5. I mean, right now frame and LC are the same. Do we know it's always going to be exactly 5 under LCL? We do actually, right? Some of the, like, we don't know how many arguments there are, how many local variables there are, but we do know that like, there's always going to be exactly these 5 things here. So we say ret equals value at frame -5. Okay, so we save those. Now I want to, I don't know, what do you think? What do you think we should do next? There's a lot of things we could do. Let's move the return value from here down to here where the caller expects to see it. So I want to say set the value at arg to or no, maybe I should say this. I'll say pop from the stack. And put value at arg. Yeah, makes sense. And again, since I'm about to clobber the stack pointer and put it somewhere else anyway, it doesn't actually matter if I literally pop, like by decrementing the stack pointer. Really all that matters is I look at, you know, one less than where the stack pointer is, and that's where I get the value from. I don't necessarily have to change the stack pointer, although again, it's a trade-off. Like, because you probably have a function to generate code to pop the stack, and it's much easier to write the translator if you just call that, even though it's slightly less efficient, because you're going to change the stack pointer and then just change it again right after. So it's up to you. If you want to optimize for your time or for the computer's time. What next? Okay, yeah, now we're going to set the stack pointer. So what should the stack pointer be set to? Matthew, what do you think?
Arg +1.
Arg +1? Yeah, I agree. And what, let's see. There's like two more things I need to do. What many things I need to do?
We can build stuff.
What was that?
We need the old stuff.
Yeah, we need to restore the old stuff, right? So we saved all those registers on the stack, we need to now restore them, so. This is pretty easy, this is just like, well, that equals value at frame minus 1. And this is the reason that I stored the frame, because, you know, I'm about to overwrite local and and I already changed the stack pointer. So, frame is the consistent way that I can refer to them now. This equals value at frame minus 2, etc. for our local. I do the same thing, right? Frame minus 3, frame minus 4. And then, what's the last thing that I did? Zach?
Don't you have to pop the arguments?
No, I don't.
Okay.
I mean, I kind of did, because I set the stack pointer to here.
Oh, so it just overwrites them.
Yeah, it doesn't, so like, all these values that we put here, that we pushed on the stack, like they're still there in memory. But the stack pointer now points to here, which means that from the point of view of the program that's running, it doesn't matter. Like, if we push more stuff on the stack, it's just gonna overwrite them as the stack pointer goes up. We don't actually have to go through and like set them to 0 or something. Conceptually they're not there, but in theory they're still there. Which is actually kind of a related reason, this is a tangent, but why, like, if you delete a file, of course, probably your operating system puts it in like the trash and it's still there. Even if you clear your trash, the file is still actually there on your hard drive. It's just like, now there's some metadata that says we're not using that area of the hard drive. So if you come along and make a new file at some point, it'll get overwritten. But there's a small window of time where it's still, the data is still literally on your hard drive. So this is both like good if you want to recover something you've actually deleted. It's if you like shut down your computer immediately. So, by the way, right, pro tip, if you ever accidentally delete a file and you realize it quickly, the best thing you can do is to turn your computer off immediately so that it doesn't like go making new files and overwriting it, right? And then like take it to an expert that knows how to recover data from hard drives. Hopefully you never need to do this, but because yeah, it doesn't literally like zero it out. On the other hand, if you have some sensitive data and you really do want it to be gone, you have to use some kind of utility that like overwrites the data with zeros or something explicitly instead of just deleting the file. Anyway, all right.
Or just try to hard drive.
So what do we need to do? What's the last thing we need to do? Matthew?
We need to go to the return address.
Yeah, we need to jump to the return address.
Oh.
Yeah. I was like, oh, that. Well, I knew, of course, that, but I thought you were asking us something else. No, we need to jump. Oh, this is the point of the class where my pen stops working temporarily. We need to jump to the return address, of course. While my pen is charging, I wanted to talk about why, let's see, yeah. Why is it important, it's a little subtle, why is it important to save the return value? Couldn't we just, at the end, say like, you know, it's like you know, if you do some math, it's like whatever the stack pointer is plus, you know, n minus 1 or something, like to get past the arguments and like the return address is going to be there. Why would that not work?
Is it because we don't have access to the number of arguments anymore?
No, we do.
Oh.
Well, I guess you're right. Yeah. That's true. We actually don't, when we're doing a return, we don't exactly know how many arguments there were. We could like figure it out by doing some math with arg and stuff like that, but But even if we did, it's still not a good idea to do that. So what if there are 0 arguments? So this is why. Because if there's no arguments, then the return address will actually be stored right here, and it's going to get overwritten by the return value. Right there. So we've got to save it first. And of course, having a function with no arguments, like that's a pretty common thing. Like that, we do that for sure. So we want that to work. We also say like a meta comment, which is obviously there's a lot of details here. There's a lot of things that you have to get exactly right, and there's a lot of ways that you can get something slightly wrong so that it totally breaks the whole thing, right? And this is not like, you know, if you get something slightly wrong, it's not like, well, calling functions almost works, but it's, you know, it's a little bit off. No, if you get something slightly wrong, it's just gonna like, stuff's gonna get overwritten in weird ways. It's gonna like jump to some address that has nothing to do with it. I mean, it's like, it's not gonna work at all. So you definitely should become friends with, you know, the simulator tools that you have, like to, and I know for this project they give you, so you should use the virtual machine simulator and also the CPU simulator. The virtual machine simulator, you can look at the virtual machine code and like kind of step through what it's kind of supposed to do conceptually, and then you can also step through what your generated assembly code is actually doing and think about how that's supposed to compare to what the virtual machine is supposed to be doing. It's definitely, it can definitely be tricky, but I'm happy to help debug. I like debugging. All right. Oh, and then one last thing. What about if we see a function, you know, name n instruction? Right, that means, hey, we're starting to define this function. This is very simple. We first say, you know, VM file dot name. So we make a label for it, and then we push 0 n times. That's to set up the locals. Right. So when the function gets called, you know, it has its arguments. It has its local will now point to a place where it may store its local variables, but we're just going to have the function set up its local variables itself, because that way it only has to happen once. But that's it. That's all. Just a label that you can jump to when you call, and then some code to push the local variables, and then after that you're just translating whatever the instructions are in the body of the function. All right. Any more questions about that? All right. So really quickly, I want to actually just demonstrate. So the other thing I think I mentioned that is different from between projects 7 and 8, besides the fact, of course, that you have to translate more instructions, but and the bootstrapping we talked about. The other thing that's different is the fact that you have to be able to deal with multiple VM files. So ultimately, the reason that we're doing this, right? We have a program written in this Jack language, just like Java, is going to consist of a collection of classes. Okay, and each class is going to be translated to one file of virtual machine instructions. And then we take a whole bunch of .vm files together, and we're going to translate them into one giant assembly program. Okay, and it's important that the reason that we do it that way is so, for example, you can mix and match virtual machine files. So maybe one virtual machine file comes from some code that you wrote that you compile. Another virtual machine file, like for example, could be the the operating system that's provided. So you can take some provided VM files and your own VM file and then like turn them all together into one big blob of assembly. So I wanted to let's see. Just do a quick demonstration of how you might set this up in Python as an example. So we're going to import the OS library. I'm going to say something like, let's make our main function. And we're going to say, input. The input is, I can't call it input, that's like a special Python thing, right? VM code equals, and the import sys argv1. So that's the first command line argument. Now, the way this is going to work is that this command line argument can either be the name of a file or the name of a directory. And if it's a file, you just translate that one file. And if it's a directory, we're going to look in that directory and find all the VM files in that directory and translate all of them. Okay. So, argument can be either a file or a directory. Say a .vm file, or a directory with multiple .vm files. Okay, either way, we're going to generate, like if it's a .vm, like if it's, foo.vm, we're going to generate foo.hack. If it's a directory named foo, we're still going to generate foo.hack. Right? It's just that we're generating assembly for all those .vm files in that whole directory. So output file is going to be something like, if I say, if I split it on a dot, and then get the 0th thing. So that's going to get rid of the dot whatever if there is one, right? There might not be if it's a directory name. And then I'm going to add, dot hack. Okay? And then, what am I going to do? I'm going to say, I had looked this up just before class, so I could remind myself how to do this in Python. So if os.path.isdir VM code else. So if it is a directory, we're going to translate all the .vm files inside it. Else just translate a single .vm file. So probably what I want to do, we'll make a function called translate VM, right? That takes a file name as input, and probably takes an output file, and it's gonna translate VM code in file name and output assembly to out file. So really what I want to do is I actually want to open the output file here. So I want to say like, this is the output file name. The output file is going to say open out file name for writing. Okay, because I don't want to reopen the output file every time I'm processing one .vm file, because that would like overwrite it. I want to keep it open the whole time, and I'm just like writing stuff to it as I'm translating. And that's totally fine, right? It's just going to like accumulate. You just like write the assembly code for the first .vm file, and then you're going to write the code for the next VM file. Right. The big thing though is we have to first say generate Bootstrap file. Okay, so the generate Bootstrap function is going to write that first Bootstrap code. That's the stuff that's going to run immediately. It like sets up the stack pointer, and then it calls sys.init. And since the first thing it does is call sys.init, it doesn't matter in what order stuff ends up in the assembly file, because it's just going to jump somewhere and call sys.init wherever it ended up, right? So that's another part of why we do that bootstrap thing. Okay, so how do we do? Okay, so this is just translate VM code. Okay, and then what do we do here? If it's a directory, then I want to say something like for file in os.listdir VM code. I think that's what it's called. Lister is a function that just gives you a list of all the files in a directory. And I just want to say something like, if file dot, I don't know, if, I honestly don't remember the Python to do this, I'll just say like, if file ends with .vm, then translate vm file. You can figure out how to check if it ends with .vm. I mean, I guess you could like call split on it, and then on with a dot, and see if see if there's a thing. Be a little careful there. There's probably actually some functions in the OS library that will get the extension of a file name or something. I'm not sure. Does this make sense? Any questions about this? Simon?
Does it matter which order they're translating?
No, it doesn't. And that's what I was saying. So the reason it doesn't matter is that everything is a function. And we first generate that bootstrap code that sets up the stack pointer and then calls the special sys.init function. From that point on, sys.init is going to call a function called main, and that can call other functions. And when you call a function, right, it just jumps to wherever the label for that function was. So it doesn't matter where in the assembly program that function ended up getting translated, right? It's just going to jump between them. And so that's part of the reason that we're doing it that way, that making everything a function, so that we don't have to worry about what order things get translated in. So you can imagine like, oh, we make sure that the main function is the first thing we translate so that happens first. But this is a nicer way to do it. This is also nice because the sys.init function, as we'll see, the sys.init function is going to do some other stuff other than just calling main. It's going to set up its own things. For example, it pre-computes some numbers to make doing math faster when you ask it to do some math things later. And so it needs to like create an array and like pre-compute some numbers and put them in there. It does a bunch of stuff to set things up, right? But that's going to kind of happen just automatically when we call it. I don't think the actual sys.init in the tests for Project 8 do not do that, because we're not actually using any of that stuff. But eventually that's what will happen. I think in the tests for Project 8, they literally, sys.init just literally calls main. That's all. But. Other questions? Yeah, Zach.
Is this the VM translator we'll be using for the rest of the class while we translate VM files?
In theory, yes.
Okay.
Now, so of course, so number one, like the materials from your book provides a VM translator. So, even if you don't quite get yours to work or something, you could still use the book's provided one, if you wanted to do other stuff. Number two, I actually tried, I was like, wouldn't it be, we built all these things, but each thing we're kind of basing it on, the book's version of the previous thing or something. I was like, can I write a Jack program and actually run it through like all the things that I've written all the way down to like, translate it, run it through my compiler, then run it through my VM translator, run it through my assembler, and then take that and like run it on top of the simulated CPU that in theory you can do that, but it turns out that it's so inefficient. It doesn't actually work in practice, sadly. Because like every layer is getting simulated on top of a simulation of the previous simulation of the simulation, and it's just like, it's like Inception, right? It's just like when you get to the bottom level, it's just like time takes like 10,000 years to do. Anyway, but yes, in theory, you could. And you certainly can do like, 2 layers at once. It's fun to actually like, yeah, when, write the compiler, compile some Jack code, and then run your VM translator on that. And like get the, but then take that and run that on top of the, their simulation. Other questions? All right. Have a good weekend. I will see you all